In this video, we want to look at a sampling distribution. And this is just kind of to get a general idea of what a sampling distribution is before we move forward and how we can use these in what we're looking at in the central limit theorem, which is what's coming next. So first, the law of large numbers tells us that if we measure enough subjects, our x bar will get very close to our mu. And if you remember, our x bar is our mean of our sample, and our mu is the mean of the population. So as we take bigger and bigger samples, as we take more data, this x bar that we get from our sample will get closer to the mu of the whole population, which makes sense. But what happens if we can't measure a huge number of subjects? What if you're looking at people across the entire United States? What if you're looking at product coming off the assembly line at Smucker's? They can't open every jar of strawberry jam and check to make sure it's the proper thing. So they can't take a huge sample. So we have to find a way where we can take a smaller sample to predict something about the rest of the population. Now, we have talked about the sample statistic. Our parameter is x bar, and our parameter of the population is mu. Remember, statistic is a sample. Our population is our parameter. Now, we have other things about these sample statistics that we can talk about. The big ones we talked about is our standard deviation. For a sample, it is S. For a parameter, it is sigma. Those are the two that we will use the most. But you do have the variance, which is just the standard deviation squared, and your standard deviation squared. And we also have the proportion. This would be the percentage. This would be the percent of students that have an iPhone, for example. And our parameter for this is the Greek letter rho, which really looks a lot like P. So we'll just kind of call that P because it's hard to really write that Greek letter. But then we need something for our statistic for our proportion. Now, because we don't want to use P, even though that's technically a Greek letter, we will use for our sample statistic proportion, we will use P hat. So these come from our sample, and these come through our population. The sample statistics, these values right here, we can find those by taking a sample. But what we want to talk about is how can we use those to be able to predict something about the whole population. So that's kind of where we're going. We kind of talked about that already. So there's three types of inference we're going to look at as we go through, and this is kind of going forward multiple chapters. So the first type of inference we have is an estimation, where we want to estimate the value of a population parameter. This is, let's go with proportion. We want to estimate what percentage or what proportion of students at Smithville High School have iPhones. So we would sample people, we would interview a few people, and we'd have a small number that we could use as our sample to predict something about everybody at Smithville. Now, you think Smithville's small? Maybe we could just talk to everybody and get a population, and then we'll know for sure. But let's say we wanted to estimate the population parameter of how many teenagers in Ohio have iPhones. Now we can't sample everybody, that's still too much. So we're going to take a sample to predict what the population parameter is. So that's estimation. The other type is testing. This is very, very similar, but takes a different kind of angle to it. So in this case, we would say, well, I think about 80%. I think 80% of teenagers in Ohio have an iPhone. So then we collect a sample, and we determine, is that claim true or false? Do we have enough evidence to say, yeah, the evidence doesn't suggest that 80% have iPhones? Now, maybe it's more, maybe it's less, but we start with some number that we then test. That's different than straight estimation, where we have no idea and we're just trying to find the value. And the last thing we can do is regression. And we've already kind of done this a little bit. We looked at linear regression and the least squares method last chapter, but we want to then use that to make more predictions and estimations than we've done so far. So we're going to come back to that at a later date. So these are the three types of things where we can use our data from our samples to infer or estimate things, make predictions about things that we want to find. To do that, we're going to use something called a sampling distribution. Now, a sampling distribution, we want to spend some time here trying to explain what this is. Here's the definition. A sampling distribution is a probability distribution of a sample statistic that is formed when samples of size n are repeatedly taken from a population. What does that mean? Okay, so we want to talk about that. First off, it's a population distribution of a sample statistic. So we could have a sampling distribution about the mean, we could have a sampling distribution about the standard deviation, whatever, about the proportion, and it's samples of a certain size. Maybe n is a sample of 10, maybe it's a sample of 100. It's a sample of some amount. So to find a sampling distribution, you have to have a set size of the samples that you are taking. So let's do an example that are in your notes, and we're going to try this with the video. So first off, I want to refresh your memory on your calculator of how to pick a random number. So if we go down here to random integers, and I say I want to pick a number between 0 and 9, I want to pick 4 of them. We could do this. Now, if you do that, it's possible you could get a repeat. So because we don't want to use repeats, if you don't have this next thing on your calculator or on your phone calculator, just hit it many times until you don't have a repeats. Or you can go down here to no repeat. I'm going to do the same thing. So you want to pick 4 numbers from 0 to 9 with no repeats. And like I said, whatever you're using, if you get a repeat, just hit enter again. Okay, so just to refresh your memory, that's how we pick random numbers. Now, we are given a set here of student test scores. So we have 10 of them. Okay. What I want you to do is I want each student using their random number generator. I have 7492. So I would have 7492, and use those 4 numbers that you get for your random sample, and I want you to find the average of those 4. Okay, so in my case here, I have 80 plus 72 plus 66 plus 62 divided by 4. So my average is 70. So I want you to pause the video here. I want everybody to do this, finding their own random 4 numbers. You shouldn't use the ones I find here. Do this on your calculator for yourself. Find your numbers, and then I want you to pause the video, and I want everybody to come up and write your numbers on the white dry erase board to the left of the smart board once everyone is done. So everybody find your 4 numbers, find your average, and write them on the dry erase board. Okay, we're back. So everybody's number is up on the dry erase board. Now, I want you to pretend for a second that we had this number line and everybody put their number. My number was 70. So I'm going to put a dot right there. I'm not sure why I put it at 69. Let me move it over to 70. Okay, put my number right there. I want everybody to come up here or pretend, and that you would come up and put your dot on this number line. Now, I have done this from past years from classes, so I'll give you an idea. Here is a class last year that everybody found their mean, and then everybody put their dot on the number line. Now, you can kind of see the shape we have here. This distribution of all of these points, this is a new sampling distribution. This is a sampling distribution of X bar. So the sampling distribution is, go back to it here, the probability distribution of all the samples that are taken from a population. So if we did this and I said I wanted everybody to do this 10 times, so everybody would have 10 averages, and then we plot all 10 on the number line over and over and over again. Here's some more, a class plotted. There's some more. Here's some more. So this is, everybody has done this a whole bunch of times. So this is all of those samples. This is a sampling distribution. Each dot, this graph, represents the mean of a sample. This doesn't represent the data. It's the mean. Now, if we were looking at this sample, this test statistic, our mean is 69.4. So we could see, here is our mean right in the middle. Our standard deviation is about 8.04. Okay? So from this, you can see from what we talked about previously, this doesn't quite match up, because this point where that changes in the curve, that is not at 8. That doesn't match up. Because this is not our curve of our original data. This is our X distribution curve. The mean is very similar, but the standard deviation is very different. And that's what we want to talk about. Okay? Now, I'm going to go through and say, let's pretend we did this again. Okay? We're going to do this again, find another sampling distribution, but we would do this with our length of fish. And then we did this a long time ago. I'm just going to talk through this so we don't have to do it. If you remember, we had this length of all of these fish, 159 fish, and let's say we went through and had everybody randomly pick 10 and find the mean. Okay, so we did that before. Okay, now if we did that and we had everybody come up and plot their point on a graph, we would get these graphs, and these are previous classes. So this graph here is not all the fish. This is an X bar distribution. This is a sampling distribution. This is each dot represents the mean of 10 fish. Now, if you go back and look at the list, you can see we have some fish that are 59, 56, 48, that are very long. But when we look at our graph, we don't have anything up there, because these dots are an average of a sample size of 10. That's the sampling distribution. Okay. Here is the histogram of all of the fish. And you can see here, this is similar, but here we have some at 50 and higher. This is an X distribution. This is a distribution for all the fish. And you can see it as a mean of 26 and a standard deviation of 10, which, once again, 26 is about there, is the high point, right? Makes sense. Standard deviation, similar, I'm off a little bit. But this graph is different. You can see the mean is still at 26, but my standard deviation is much smaller. There's not as much variation because each point is the average of a sample. And because it's the mean of a sample, it's taken out all the highs and lows, and all of these points are really close to the mean. That is a sampling distribution. That is how a sampling distribution works. Now, let me give you another visual here of how this would work. So, let's say this top distribution is all of our fish or all of our people. It's our parent population. And this has a mean of 16 and a standard deviation of 5. Now, let's say I have a sample of 5. Down here you can see my n is 5. And I'm going to take a sample from this distribution at the top. So I click animate, 1, 2, 3, 4, 5. And then this blue dot down here is the mean of that sample. Let's take another sample. 1, 2, 3, 4, 5. Blue dot's the mean. Let's take another sample. 1, 2, 3, 4, 5. Blue dot's the mean. Let's take another one. 1, 2, 3, 4, 5. Blue dot's the mean. Okay? And so we can do this over and over. Instead of you using random number on your calculator and doing the calculations, this program's doing it for us. And we can just keep going and so forth. Now, instead of doing that one at a time, if I clear these and just click 5, it has 1, 2, 3, 4, 5. It did it 5 times. If I click 10,000, it just did 10,000. Now you will notice the mean, the center, the peak of this is still 16. But my standard deviation is much smaller because when I'm averaging this population in each sample, that averaging takes out the highs and lows, and there's not as much variation. Now, depending on your sample size, will change what your graph looks like. So let's say we take the mean again, and let's say we take a sample of 20. And I do 10,000. You will notice the mean stays about the same, but standard deviation is smaller because when you take a bigger sample, you average out everything, there's less variation, you have a smaller standard deviation. So this is our first kind of understanding of what a sampling distribution looks like. Still no homework over this. We will go to continue on here with the next video, and we will look at understanding how we can use this to make some calculations. Let's continue and look at the central limit theorem. So we're going to build off the first part of this video where we talked about a sampling distribution, and this is going to lead us into the central limit theorem. So as we talked about last time, why do we care about sampling distributions? Well, if we think of a continuous random variable from a population we want to study, we can't necessarily sample huge amounts of people, right? So we want to think of a way we can possibly do that with our sampling distribution. So if you remember, if I go to my graph here, this was our idea of a sampling distribution, whereas if we have some population, this is all the people in Ohio or in the United States, and we take a sample of, let's say, size 10. We take a whole bunch of samples, 10,000 of them from around the country, and we find the average, and this is our new distribution. This is a distribution of the means. That is what our sampling distribution is. Okay? So that's what we want to look at. So we looked at the examples of the fish the last time. I just did the example online. And so we remember there's a difference between the sample and the population. And we said the mean of the sample and the population, if we look here, the mean, if I take, let's go back to our sample of 5. If I take 10,000, you can see that our mean is almost exactly the same. And if I take more, it eventually basically becomes the exact same thing, right? It basically becomes 16. However, my standard deviation is smaller. This went from 5 to 2.23. So the question is, how does our standard deviation change? It gets smaller because we're finding the average. It varies less. So to summarize, here is a theorem that we have that's going to tell us what's going on. So first off, for a normal probability distribution, let x be a random variable who is normally distributed with a mean, mu, and a standard deviation, sigma. So that is this top. This is our normal distribution. It has a mean and it has a standard deviation. So if we have that true, then we know the following. Let x be a sample, xx bar, be a sample mean corresponding to a random sample of size n taken from that distribution. So if we look here, size n is 5. We're going to take sample, and this now new is our distribution of x bar. Okay. Here's what we know. This new distribution is also a normal distribution, which you can see from here. It looks to be just like the other one. Now it's skinnier, but it's still a normal distribution. So that's our first thing that happens. Number 2, the mean of this x bar distribution is also mu. We can see that. Our mean is 16, our mean is 16. Now this is only 10,000. We may have to do more, but if we took all of these, it eventually would be equal to 16. Now, what about the standard deviation? The standard deviation is this. The standard deviation of the x bar distribution is sigma divided by the square root of n. So that tells us what this new distribution is. So if we look here, we had 5. Our sample size was 5. So if we take 5 divided by the square root of 5, our new distribution is 2.23. And you can see we had 2.22. If we have a bigger sample, let's do a sample of size 20. You can still see our our mean is 16. Now our standard deviation has gone to 1.12, so that would be, we had 5 divided by the square root of 20, which is 1.12, which is our new standard deviation. So when we construct these sampling distributions, we now know that for this sampling distribution, our mean stays the same as the original distribution, and our standard deviation is sigma divided by square root of n. Okay. Now, the way we denote this, the way we denote the mean of the means, so to speak, right, is we denote this as the mean of the means is still mu, and our standard deviation of those means, the sampling distribution, is sigma over the square root of n. Now the way we denote this is we say mu x bar, that's the mean of the sampling distribution. It's the same thing, but we still write it. And then this is sigma x bar. So if we have a new distribution, these are our new things. So what that gives us, mu x bar is just equal to mu, sigma x bar is just equal to sigma over square root of n, and if we wanted to do this, we could now get a new z-score, and we can go through and use that to do our calculations like we did previously. Now, one thing I want to mention before we find this is the idea of a standard error. This is sometimes this sigma x bar, or sigma over square root of n, is known as the standard error. What this means is the standard deviation of your sampling distribution, you can determine it by kind of determining what n is. So if we come back to here and you're like, okay, I want my sampling distribution to have a standard deviation at 1. Okay, then you can say, well, how big of an n do I need to get my standard deviation closer to 1? Well, if I want it to be closer to 1, if I make my standard deviation, if I make my sample 25, 5 divided by the square root of 5, I should get a standard deviation of 1. So this sampling error lets you determine that by determining what your n is. Now, as we do this, you can see as n gets bigger, our standard deviation gets smaller because you're dividing by that square root of n. So let's look at an example and see how all this connects. The time it takes to drive between cities A and B is normally distributed with a mean of 14 and a standard deviation of 2.2. Find the probability the trip between the cities takes more than 15 minutes. So this is, what's the probability that x is over 15? Now, like we looked at last time on our calculator, we can just do this on our calculator. This is just normal CDF. We have 15 to 99999. Our mean is 14, and our standard deviation is 2.2. So if we go to our calculator, and we have normal CDF, and we have our lower is 15, our higher is 99999, our mean is 14, and our standard deviation is 2.2. So if we paste that, we get 0.325. That is exactly what we did on the quiz for the earlier. This is what we did last week on the calculator. So that's nothing new. Now let's look at how this can be different. Find the probability that the mean time of 9 trips is more than 15. And this is why I've been mentioning what the variables come in. This is now, what's the probability that x bar is greater than 15? And this changes a little bit because now our mu for x bar stays the same, and it's 14, but our sigma for x bar becomes sigma divided by the square root of n, which is 9. So this is 2.2 over 3. So now, when I type this in, normal CDF, 15, 99999, 14, 2.2 over 3, we get our new probability. Now you would imagine, if we think of this 14, right? If we kind of connect this with what we did before, if we said here is our 14, what's the probability it's greater than 15? We found the answer. But we know when we do this with our sampling distribution, our standard deviation is smaller, so this is narrower, and so it's more grouped together. So at 15, we should get a smaller answer because less of the averages, less of the means are greater than that. And all we really need to change down here is we need to come here and divide by 3, and we get 0.086. So it is smaller because we are now looking at the mean of 9 trips. So we want to make sure we understand the difference between when is it x bar, a single trip, and when is it the mean of a sample. Okay? That's where we're going to stop today. We can do the first homework over 5-4.